Massive wooden ships once crossed oceans without a single iron nail. This was the true power of ancient shipbuilding, a craft so advanced that modern engineers are now scrambling to decode its secrets. By the end of this journey, you will understand 40 forgotten techniques that are revolutionizing sustainable design. How did a 2,000-year-old hull remain stronger than modern steel? What timeless wisdom allowed these vessels to survive storms that would shatter today's ships? Is it possible that our most brilliant future innovations are actually waiting for us in the past? A modern engineer stares at a shipwreck recovered from the Mediterranean seabed, a vessel over 2,000 years old. Its wooden planks, devoid of any metal fastenings, have outlasted entire empires. This single moment of bafflement has ignited a global quest, a paradigm shift where the pinnacle of innovation is no longer about creating something entirely new, but about understanding an old mastery we lost. We are moving from an age of pure invention to one of profound rediscovery. A leading maritime archaeologist put it best, stating that we are not just discovering old techniques, we are rediscovering a different philosophy of design, one that worked in harmony with nature instead of trying to dominate it. This renaissance is driven by urgent modern needs. Our synthetic materials often fail over time, requiring constant replacement. The energy cost of producing modern steel and composites is staggering. We are actively searching for sustainability, for material efficiency, and for resilience against new challenges like stronger storms and rising seas. Consider ancient Roman concrete used in seawalls and harbors. While our modern concrete crumbles in saltwater, the Roman version actually grows stronger over centuries, a self-healing property our scientists are still struggling to fully replicate. This is the core of the rediscovery phenomenon. What if the most elegant solutions to our pressing engineering problems have been resting silently at the bottom of the sea for millennia? This reflection brings us to the first of these remarkable techniques, a fundamental principle that defined seaworthy vessels for ages. That skeleton of a Greek trireme was held together by a principle of perfect fit. Its planks were interlocked with an ancient woodworking method known as the Mortise and Tenon joint. Think of it as a three-dimensional wooden puzzle. A craftsman would carve a precise rectangular peg, the tenon, on the edge of one plank. This tenon would then be hammered tightly into a matching slot, the mortise cut into the edge of the neighboring plank. The result was a hull that acted as a single, unified shell, a monocoque structure that moved with a living flexibility. A shipwright working on a historical recreation described it perfectly, saying the wood moves with the sea, it breathes, whereas metal fastenings fatigue and fail. This breathing quality was its genius. Instead of concentrating the immense forces of the ocean on rigid metal nails, the Mortise and Tenon system distributed stress evenly across the entire framework. It prevented the catastrophic failure points that could tear a riveted ship apart in a storm. This was not crude joinery. It demanded the highest level of precision carpentry. Each joint had to be carved to tolerances we would associate with fine furniture, not a massive seagoing vessel. And they often used a clever trick, selecting woods like oak that would swell slightly upon contact with water, creating a naturally watertight seal that grew tighter the longer the ship was at sea. The proof of its resilience lies on the seabed. The Kyrenia shipwreck, a merchant vessel from around 300 BC, spent over 2,000 years submerged. Its hull, assembled with thousands of these wooden joints, remained largely intact, a silent testament to a connection method that outlasted empires. How many of our modern structures, reliant on bolts and welds, could claim such longevity? This mastery of wood led to another ingenious method of hull assembly, one that took flexibility to its logical extreme. This shell-first method turned conventional wisdom completely on its head. Instead of building a rigid skeleton and then attaching a skin, ancient shipwrights began with the skin itself. They would carefully join the planks edge to edge, creating the complete outer form of the vessel before a single internal frame was installed. It was an act of sculpting a hollow form from the waterline down, a process that required an intuitive, almost artistic understanding of how the final shape would interact with the sea. A naval architect studying Viking longships observed that this method produced a hull with immense torsional strength, allowing it to flex over waves rather than break. Think of the difference between a rigid ruler and a woven basket. You can twist the basket easily, and it returns to its original shape. The ruler, if twisted too far, simply snaps. A shell-first ship was that basket, a unified, flexible structure that could ride the ocean's swells instead of fighting them. This organic development meant the hull's form was not dictated by a preconceived blueprint, but emerged from the planking process itself, resulting in vessels perfectly adapted to the specific conditions of their intended waters. The execution of this vision varied brilliantly across the ancient world. In the stormy North Sea, Viking shipbuilders perfected clinker construction, where each plank overlapped the one below it, creating a ridged, incredibly strong hull that could bend and twist with the violent motion of the waves. Meanwhile, in the calmer Mediterranean, shipwrights favored Carvel construction, fitting planks flush against one another for a smooth, hydrodynamic surface ideal for speed and trade. Both methods, however, shared the same core philosophy: build the shell first. The Oseberg Viking ship, excavated in Norway, stands as a breathtaking example. Its gracefully overlapping planks sweep upward into elegant spirals at the bow and stern, a form born entirely from the planking process. There is no distinction between the structural frame and the aesthetic shape. They are one and the same. Could this fluid, form-following function approach inspire more adaptive modern designs for our own turbulent seas? The incredible strength of this hull, however, depended entirely on what held those planks together. Those wooden planks were not simply joined, they were often bound together by the very sinews of the earth itself. Before the age of iron nails, the true strength of a ship came from its lashings, a complex web of rope made from papyrus, coir, or animal sinew. Think of a massive Egyptian vessel, its hull not a rigid cage of metal, but a dynamic structure held fast by thousands of these organic cords. This technique offered a different kind of genius, one of dynamic strength. The lashings were not meant to be immovable. When soaked with seawater and placed under the immense load of cargo and waves, these natural fibers would tighten. They created a hull that could work with the sea, its components constantly shifting and adjusting to pressures, a quality completely absent in a rigid, welded hull. An expert in ancient materials describes a lashed ship as a living entity, its parts always in a subtle dance with the ocean. The choice of fiber was a science in itself. In Egypt, they used papyrus, while in the Indian Ocean, shipwrights relied on coir, a resilient fiber from coconut husks that is remarkably resistant to rot in salt water. These materials were not weak substitutes, they were carefully selected for their specific properties. The knotting techniques were equally sophisticated, employing secure, self-tightening knots that ensured the entire network remained taut and reliable across thousands of miles of open ocean. This method was universal, from the bundled reed boats of Lake Titicaca, lashed together to navigate the high-altitude waters, to the great funeral barks of the pharaohs. This principle of binding was foundational. The most stunning proof is the Khufu ship, a vessel buried for 4,500 years next to the Great Pyramid. When it was discovered, its intricate system of lashings was found virtually intact, the cords still holding the cedar planks in perfect alignment after millennia. In our modern era, which desperately seeks repairable and modular design, what profound lesson can we learn from a structure designed not for permanent, rigid assembly, but to be taken apart, its components inspected, replaced, and reassembled with simple tools? This reliance on organic materials, however, extended far beyond ropes and into the very bones of the ships themselves, leading to the discovery of timber so remarkable it was considered a strategic resource. The very trees they felled held a secret, a hidden potential unlocked only by building with wood that was still alive. Ancient shipwrights often preferred green timber, wood freshly cut and still brimming with natural sap and moisture. This seems counterintuitive as we associate seasoned, dry wood with stability and strength, but for bending the dramatic curves of a ship's hull, that internal moisture was the key. A green plank was incredibly pliable, allowing craftsmen to steam and coax it into shapes that would have shattered a dry, brittle board. A traditional boat builder describes this process as working with the tree's memory. You persuade the wood into its new form, and as it slowly dries in place, it locks into that shape forever. The result is a hull with a kind of organic, set strength that is incredibly difficult to achieve any other way. This was not a haphazard choice. It was a precise science of selection and timing. Builders chose specific species like oak or elm for their bending qualities. They often felled trees in the winter when the sap was down, or even followed lunar cycles, believing it optimized the wood's workability and resistance to rot. The construction itself was a race against time, a carefully orchestrated process where the green planks were bent into position and fastened before they could dry and set. After the hull was complete, it would undergo a controlled drying process, often in a humid environment or even partially submerged, allowing the entire structure to find its final, locked-in form as a unified whole. This method had a brilliant side effect. It minimized the internal stresses that plague modern, kiln-dried timber. When you force dry wood into a curve, it fights back, creating tension points that can lead to cracking and failure over time. But a hull built from green wood experiences no such shock. It simply becomes what it was always meant to be. The proof lies in the anoxic depths of the Black Sea, where ancient Greek shipwrecks rest perfectly preserved. Analysis of their planks reveals the telltale compression patterns of wood that was worked while still green, a silent validation of a practice once thought to be mere folklore. In our world of processed, standardized materials, have we forgotten how to listen to what the raw substance itself is telling us? This profound understanding of wood's living nature was just the beginning. The next step was to master its final, permanent form through an alchemy of fire and water. The transformation of a straight plank into a ship's elegant curve was an act of controlled alchemy. Ancient shipwrights mastered the art of steam bending and heat forming, using fire and water to persuade wood into shapes that defied its natural grain. In shipyards across the ancient world, planks were heated over open fires or steamed in clay ovens until they became as supple as leather. At that perfect moment of plasticity, teams of workers would heave the glowing wood over a curved form, twisting it into the dramatic sweep of a stem or the complex arch of a sternpost. The secret to this magic lies in lignin, the natural polymer that acts as the glue binding wood fibers together. The application of intense heat and steam temporarily breaks down this lignin, allowing the fibers to slide against one another and assume a new, permanent shape as they cool. A modern engineer attempting to replicate this process described it not as crude carpentry, but as a form of precision engineering. They achieved with a fire and a mold what we now do with million-dollar hydraulic presses and composite autoclaves. The methods varied with local ingenuity. Some cultures used simple steam boxes, while others packed hot sand around the wood to apply a deep, even heat that prevented scorching and internal weakness. The Phoenicians, master traders of the Mediterranean, relied on this technique to create their famously graceful hulls. Their ships required extensively bent frames and planks to achieve the sleek, hydrodynamic forms that gave them a speed advantage over their competitors. This was not a brute force operation. It demanded an intimate feel for the material, knowing the exact moment to apply pressure, the precise amount of steam, and the correct cooling time to lock in the strength of the timber. The result was a hull with far fewer seams and joints, carved from single, continuous pieces of wood that distributed stress along their entire length. When we consider the massive energy required to form modern composite materials in giant ovens, the efficiency of this ancient thermal manipulation is staggering. How can we reintroduce such low-tech, high-skilled processes into our contemporary quest for sustainable manufacturing? Once shaped, this carefully formed wood faced its greatest enemy, the relentless sea itself. The air in a Phoenician shipyard would have been thick with the sharp, clean scent of boiling pine tar. This was the final, crucial step in a ship's berth, the process of caulking that transformed a joined wooden structure into a watertight vessel. Workers moved with practiced efficiency, pouring and brushing these hot, viscous sealants into every seam between the planks, creating a flexible, impenetrable barrier against the sea. But this was far more than just plugging gaps. It was one of humanity's earliest and most successful forays into chemical engineering. A chemist analyzing these ancient residues would point out that these were not simple glues. They were sophisticated composite materials deliberately formulated with properties we strive for today. The pine pitch contained natural antiseptics that fought off the fungi and bacteria causing rot, while bitumen, a tar-like substance from natural oil seeps, created a physical shield against wood boring worms and other marine life. This was a preservative treatment and a waterproofing system in one, designed to protect the ship's very soul for decades on the open ocean. The sourcing and preparation of these materials was a specialized craft in itself. In the vast pine forests of the Mediterranean, workers built special kilns to slowly burn resin-rich wood in a low-oxygen environment, a process called destructive distillation that yielded the purest, most potent tar. Meanwhile, in Mesopotamia, builders harvested bitumen from great natural seeps where it bubbled to the surface, then mixed it with chopped reeds or minerals to create a thicker, more durable paste suited for the rivers and canals of the region. The recipes were closely guarded secrets passed down through generations. Some blends included animal fats or plant oils to adjust flexibility, ensuring the sealant would not become brittle in cold water or melt away in the tropical sun. The evidence of its importance is literally etched in history. The Uluburun shipwreck, a Bronze Age merchant vessel that sank off the coast of Turkey, carried a portion of its cargo in large jars filled with raw resin. This was not trade goods, but the ship's own repair kit, a vital supply for making emergency patches to the hull during its long and perilous journey. Today, as we grapple with the environmental toll of synthetic, toxic antifouling paints and plastic-based sealants, these ancient recipes present a compelling question. Could the path to greener maritime technology be found in these natural, biodegradable composites? We spend millions developing chemical coatings to keep marine life from clinging to hulls, yet here was a system that achieved a similar result using the Earth's own chemistry. The hull was now sealed, a protected shell ready to face the sea, but its journey was not just across the surface, it was into the depths and back, a cycle of loading and movement that put immense strain on its back. How did ancient designers ensure their vessels could carry staggering weights without simply breaking apart under the pressure? The hull of a Roman merchant ship presented a paradox, its wooden planks protected by a skin of poisonous lead. This was not for decoration, but a ruthless and brilliant defense against two silent killers, the relentless worms that bored into wood and the clinging organisms that could slow a ship to a crawl. In an age without dry docks for regular cleaning, this metal sheathing was a form of proactive armor, a one-time application that could extend a vessel's life by years. A marine biologist studying this practice would note that the lead created a toxic surface for marine life, a brutal but effective solution millennia before modern antifouling paints, which often leach copper and other biocides that harm the wider ecosystem. The execution was a feat of ancient metallurgy. Artisans hammered lead into thin, malleable sheets. These were then carefully overlapped and fastened to the hull with thousands of copper nails, creating a continuous, impenetrable barrier. The copper nails were a clever choice, resistant to corrosion in a way iron would not have been, preventing unsightly rust stains and weakening of the fastenings. This practice evolved over centuries. While the Romans perfected lead sheathing, later shipwrights, recognizing lead's toxicity to the workers who handled it, would eventually transition to copper sheathing, which offered similar protective properties. The sheer ambition of this technique is best seen in Emperor Caligula's massive Nemi ships, enormous pleasure barges whose hulls were entirely encased in lead. These floating palaces were a testament to the Roman drive to conquer not just the sea, but its very biology. The legacy of this approach is a challenging one for modern engineers. We face the same problem, biofouling, which dramatically increases fuel consumption for today's global shipping fleet. But we also recognize the environmental cost of poisoning our oceans. So the question becomes profound: how can we capture the proactive, long-lasting principle of metal sheathing without its toxic legacy? Could we develop smart, non-polluting surfaces that mimic the slick, inhospitable nature of lead? This external armor was only one part of the equation, however. The true test of a ship's strength came from within, from the hidden skeleton that gave it the resilience to carry the world's riches. A master shipwright's true material was not just wood, but the very shape of the forest. He walked among the trees, searching not for straight, perfect logs, but for the wild, organic curves of a ship's skeleton. These were the compass timbers, pieces where a branch met the trunk at a perfect right angle, or where a trunk itself had grown into a natural arch. The genius of using these grown timbers lay in the uninterrupted flow of the wood grain. When you take a straight piece of oak and steam, bend it into a knee, you are forcing the fibers against their natural alignment, creating inherent weakness. But in a compass timber, the grain follows the curve, making it a single, monolithic piece of incredible strength. A forestry expert would note that this required a profound knowledge of tree growth and an artist's eye for potential form, skills that have faded in our world of standardized milled lumber. The process was one of mapping. A shipwright would walk through a wooded area and mentally assemble a ship, tagging specific trees for specific parts. This oak with its sharp crook would become a crucial knee supporting the deck. That elm with its gentle sweep was destined to be a critical frame. This was not just about strength, it was about supreme material efficiency. By using the tree's natural architecture, builders minimized waste, often utilizing parts of the tree that a modern mill would simply discard as scrap. The Viking shipbuilders were absolute masters of this. In the Skoldilev ships recovered from a Danish fjord, archaeologists found frames and knees that were clearly carved from single, carefully selected branches and crooks. The grain in these pieces follows the curve so perfectly that they seem to have been grown for the purpose. In our age of engineered glulam beams and laminated composites, we spend immense energy and technology to recreate the very structural integrity that a tree can grow on its own. Are we overlooking the ultimate, self-assembling composite material by failing to see the strength in a tree's natural form? This philosophy of listening to the material extended even further, to a point where the ship's structure was not just built, but strategically grown into existence over generations. A master shipwright's most powerful tool was not a blueprint, but a simple, personal measurement, the length from his elbow to the tip of his middle finger. This was the rule of thumb, a living standard that defined every curve and line of the vessel taking shape in his yard. There were no complex calculations, only a set of proportional rules passed from master to apprentice, a system so refined it could produce a perfectly balanced hull from a single starting measurement. The entire ship was a cascade of these ratios, its beam a certain proportion of its length, its depth a fixed fraction of its beam. A historian of technology describes these unwritten codes as algorithms encoded in tradition, a distilled wisdom from generations of observing which shapes survived the sea and which did not. This was an empirical science of hydrostatics and stability, perfected through centuries of trial and error. Different cultures developed their own sophisticated systems. In the Mediterranean, builders used symbolic marks on a plank, a kind of ancient plimsoll line indicating the optimal loading depth for different seasons and sea conditions. Norse shipwrights worked in units called ells, often based on the master's own arm, ensuring every part of the longship was in harmonious proportion, creating a vessel that was neither too tender and prone to capsizing, nor too stiff and uncomfortable in a swell. The most stunning example of this proportional genius is the Portuguese Carvel. Its design was a masterpiece of balance, with a length-to-beam ratio that gave it both the stability to carry supplies across an ocean and the agility to sail close to the wind and explore uncharted coastlines. It was this perfect set of proportions, not a revolutionary new material, that truly enabled the age of exploration. In our era of digital modeling and finite element analysis, we can simulate every stress a hull will face, but have we lost the intuitive feel for the sea that was baked into these simple, human-centric rules? This intuitive design could only take a ship so far. Its true potential was unlocked by the invisible force that filled its sails. The deck of an ancient galley was a machine of muscle and rhythm, its power channeled through meticulously carved openings in the hull. The design and laying of the oar ports was a masterclass in integrating human power with hydrodynamic form. This was not merely about cutting holes in a ship's side. It was a precise calculation that balanced speed, maneuverability, and the critical need to keep the sea on the outside. An expert on classical warfare describes the arrangement of oar ports in a trireme as being as calculated as the cylinder layout in a modern engine. It was the heart of its propulsion system. The solution was a staggered, multi-level arrangement. In a Greek trireme, oars were deployed from 3 tiers, not one above the other, but positioned in a complex interlocking pattern that allowed the oars of the upper levels to swing through the space between the oarsmen below. This maximized the number of rowers in a relatively narrow hull, creating a dense, powerful engine. But each of these openings was a potential gateway for disaster. To seal them, shipwrights used leather patches greased and fitted snugly around each oar. As the oar swept back and forth, the leather formed a dynamic, watertight seal that moved with the rower's motion. The port itself was not a crude circle, but an oval or keyhole shape, carefully carved to minimize the disruption of water flowing past the hull, reducing drag to an absolute minimum. This system evolved over centuries, from the single bank of oars on early Egyptian vessels to the overwhelming power of the Roman quinquereme. The proof of its genius was demonstrated by the Olympias, a modern, full-scale reconstruction of an Athenian trireme. When its crew of volunteers found the rhythm, the ship surged forward, achieving speeds of over 9 knots, a velocity that would have been more than enough to smash through an enemy's hull in a naval battle. In an era obsessed with fuel efficiency and hybrid power, what profound lessons can we learn from a propulsion system that was entirely human-powered, yet so perfectly integrated with its vessel that it became a single, living entity? The graceful power of the oar was one thing, but for a ship to truly conquer the open ocean, it needed to harness a far greater and more unpredictable force. That triangular Lateen sail, slicing through the air like a razor, gave ancient mariners a power that seemed to defy nature itself, the ability to sail almost directly into the wind. While square-rigged ships were often trapped by prevailing winds, forced to wait for a favorable breeze, a vessel with a Lateen rig could point its bow within 45 degrees of the wind's direction, creating a new world of maritime possibilities. The secret lies in a principle we now call aerodynamic lift. A modern sailor experimenting with ancient rigs described the Lateen as essentially a vertical airfoil, providing lift and drive in a way we are only now fully appreciating with modern wind tunnel tests. As the wind flows over the curved surface of the taut sail, it travels faster over the outward-facing side, creating an area of lower pressure that literally sucks the sail forward. This forward pull or lift is the same force that keeps an airplane aloft, and it allowed these ancient ships to generate propulsion from an angle that would have left a square sail flapping uselessly. Its rigging was a masterpiece of elegant simplicity. The long, diagonal yardarm from which the sail hung could be pivoted and tilted with just a few lines, allowing a small crew to constantly adjust the sail's angle to capture the slightest breath of wind. This versatility made it the engine of choice across the ancient world. Its origins are debated, but it spread with traders, appearing on Roman vessels in the Mediterranean and becoming the iconic sail of the Arabian dhow in the Indian Ocean. The dhow, still built and sailed today using centuries-old methods, is a living testament to the enduring genius of this design. Its captains can navigate the complex monsoon patterns with an agility that would astonish a modern container ship. In our urgent quest for renewable energy, this ancient technology poses a profound question. The Lateen sail is a hyper-efficient device for extracting energy from a fluid flow. Could its fundamental principles, refined over 2,000 years, inspire the design of next-generation wind turbines that are quieter, more efficient, and able to capture power from gentler, more variable breezes? That delicate dance with the wind, however, demanded an equally responsive system of control at the ship's stern. A single sailor, standing firmly on the deck, could command the entire sail with a handful of line. This was the power of the Brailed rig, a system of ropes that ran from the foot of the square sail up through rings sewn into its face and back down to the deck. By pulling on these brails, the crew could gather the sail upwards like a curtain, instantly reducing its area to weather a sudden squall or to spill wind and slow the ship's headlong rush. This was reefing made safe and swift, a dramatic leap in maritime control. A maritime historian would call this an early form of automation, where 1 or 2 men could manage the entire power plant of the ship without ever leaving the deck. The safety implications were immense. In an era before safety harnesses, climbing a swaying mast in a storm was a death-defying act. The brailing system eliminated that need, keeping the crew secure while they performed critical maneuvers. The materials themselves were a testament to their purpose. The lines were typically made of durable, flexible linen or hemp, strong enough to take the strain yet soft enough not to chafe through the sailcloth. The rings, often carved from antler or fashioned from bronze, were smooth and robust, designed to guide the ropes without snagging. We have direct evidence of this from shipwrecks like the Kyrenia merchantman, where archaeologists discovered those very rings amidst the timbers, silent proof of a system that gave a small crew mastery over a vast sail. This innovation did not remain static. It evolved over centuries, becoming more refined and efficient, a clear precursor to the complex line systems on later square-rigged vessels. In our modern world, where we often design machinery that requires specialized tools and shutdowns for simple adjustments, the Brailed rig poses a fundamental question. How can we design our own complex mechanical systems, from wind turbines to factory robots, to allow for easier, safer, and more immediate human intervention? The ability to quickly manage power is one thing, but to truly navigate, a ship must be able to hold its course against the push of wind and wave. That massive steering oar was more than just a lever. It was an extension of the helmsman's own body, a direct physical connection to the water flowing past the hull. Before the central sternpost rudder became standard, ships were guided by one or two of these colossal oars mounted on the quarters, the sides of the vessel near the stern. Picture an ancient Egyptian sailor, his hands gripping a weathered shaft, heaving his entire weight to guide a cargo ship down the winding Nile. This system was physically demanding, yes, but it offered a level of tactile feedback and immediate control that modern hydraulic steering can only dream of. The secret was its mechanical elegance. A naval engineer observing a reconstruction would note that the quarter rudder's pivot point creates a powerful turning moment. By leveraging the water pressure against the large blade, a single helmsman could swing the entire mass of the ship, and its failure mode was beautifully graceful. If a rogue wave or hidden obstacle shattered one oar, you simply switched to the spare mounted on the opposite side, a built-in redundancy that could mean the difference between survival and disaster. The construction of these oars was an art. They were carved from a single, massive piece of resilient wood-like oak, their blades broad and flat to catch the maximum amount of water. They were mounted on heavy wooden posts or through specially reinforced holes in the hull, secured with leather grommets that allowed them to pivot smoothly while keeping the sea out. To reduce the immense physical strain, Viking shipwrights developed a brilliant solution, the styrie or beitas. This was a wooden block, often carved with intricate patterns, that was lashed to the loom of the steering oar. It acted as a fulcrum, giving the helmsman a critical mechanical advantage and allowing him to steer the massive longships for hours on end. The effectiveness of this system is proven by the Vikings' own feats. Their steering oars allowed for breathtakingly precise navigation through the treacherous, narrow fjords of Norway, environments where a single misjudgment would dash the ship against granite cliffs. In our world of overcomplicated electronic control systems that can fail with a single power surge, the quarter rudder poses a stark question. What is the true value of a redundant, simple, and utterly dependable mechanical control? Steering the vessel with such an intimate tool required more than just muscle, however. It demanded a deep, almost instinctual understanding of the environment, a knowledge passed down through generations of ancient navigators. A Polynesian navigator, blindfolded, could still feel his way across the ocean by the subtle dance of the hull beneath his feet. This profound connection between the ship and the sea defined the 14th technique, a symbiotic relationship where the vessel's very design was an extension of celestial and environmental navigation. The double-hulled canoe, or wau, was not just a boat, It was a floating observatory, its stability and shallow draft allowing a navigator to sense the faintest refracted swell bouncing off an unseen island dozens of miles away. Its design was a direct response to the navigational method, creating a platform perfectly suited for reading the language of the sea. A modern navigator studying these methods described it as using the planet itself as a GPS, a level of situational awareness we are only now trying to replicate with complex satellite networks. The tools of this art were etched into the natural world. The Polynesian star compass was not a physical object, but a mental map of the rising and setting points of key stars, dividing the horizon into 32 directional houses. Navigators memorized this celestial map, knowing that as one star set, another would rise to guide them, creating an unbroken chain of cosmic waypoints across the night sky. In the foggy North Atlantic, Viking sailors employed the sunstone, a crystal of calcite or cordite that could polarize sunlight, revealing the sun's position even through dense overcast. They combined this with a detailed knowledge of migratory bird paths and the distinct color of sea ice, weaving together multiple threads of environmental data. This mastery extended to the very winds. Arab and Indian ocean traders did not fight the monsoons. They designed their dhows to ride these predictable, seasonal reversals, their voyages timed to the turning of the Earth itself. The ultimate proof of this ship-skill symbiosis is the human settlement of remote Oceania. The colonization of islands from Hawaii to New Zealand was not a series of accidental drifts, but the greatest navigational feat in human history, a deliberate expansion across thousands of miles of open ocean in vessels that were both home and instrument. In our age of digital fragility, where a single solar flare can disable our global positioning networks, what profound resilience might we regain by relearning these analog systems that use the stars, the waves, and the wind as their eternal, unfailing signal? This self-sufficiency at sea demanded more than just navigational skill. It required a vessel that was a veritable floating fortress, engineered to withstand the ocean's relentless attempts to tear it apart. The hull of a merchant ship was a living ecosystem, its belly a carefully managed balance of fresh water, heavy ballast, and precious cargo. This was not mere storage, it was an integrated system where every element served multiple, vital purposes for survival at sea. An archaeologist studying shipwrecks observes that we find amphorae not just as cargo containers, but often strategically placed to act as ballast, and the ship's structure itself was designed to catch and store rainwater. The ship's design was a holistic solution to the twin demons of long voyages, thirst and instability. The bilge, the lowest part of the hull, was the operational heart of this system. Here, water that seeped in or sloshed from cargo was constantly managed. Simple but effective pumps, operated by hand or even foot pedals, would lift this water up and out, keeping the ship buoyant and preventing cargo from being spoiled. The ballast itself was a dynamic element. Instead of permanent, dead weight, many ships used shingle ballast, smooth stones that could be shifted to adjust the ship's trim for different sailing conditions. This shingle could even be brought ashore and cleaned of salt and organic waste, then reused, a perfect example of circular economy thinking from millennia ago. But the true genius was in water storage. The Magan Michael ship, a wreck discovered off the coast of Israel, had a hull design that subtly sloped to funnel every precious drop of rainwater to a central collection point. Internal tanks, sometimes lined with tar or massive casks, were positioned low in the hull. This served a dual purpose. It provided the crew with vital drinking water, while simultaneously acting as fixed, low weight that enhanced the vessel's stability. Every single component was pulling double duty. A stack of amphorae filled with olive oil was not just profit, it was carefully calculated ballast. A full water cask was not just a supply, it was a structural member adding rigidity to the frame. In our modern world of single-function shipping containers and complex, separate systems for water and waste management, this ancient, integrated philosophy is a powerful challenge. How can we design our own transport, from cargo ships to long-haul trucks, to achieve this level of multi-functionality and resource efficiency, where waste is minimized and every element serves more than one master? Keeping this delicate balance required more than just smart storage. It demanded active, relentless work to fight the sea's constant intrusion. The rhythmic groan of a wooden pump was the sound of a ship fighting for its life. Deep in the hold, a crew member would work the handle of a reciprocating pump, a simple piston of wood sealed with leather that drew water up through a pipe and spilled it back into the sea. This relentless, back-breaking task was the frontline defense against sinking, a manual battle against the ocean's constant intrusion. A specialist in ancient mechanics would call these devices marvels of practical engineering, capable of moving surprising volumes of water with human power alone. The most common design used a hollowed-out log or a wooden box as the pump chamber. Inside, a leather-covered piston created a seal, and simple one-way flap valves, often made of leather or a flexible wood, ensured the water only flowed upward. With each stroke, the sailor was not just moving water, he was buying the ship another mile, another hour, another day. Archaeological finds reveal an evolution in this crucial technology. While the basic bucket chain was a fallback on every vessel, more sophisticated designs emerged. The Romans perfected the reciprocating force pump, with bronze cylinders and pistons that could direct a powerful jet of water. Later, the screw pump, often attributed to Archimedes, found its way onto larger ships, its turning helix lifting water in a continuous, if labor-intensive, flow. The true mark of its importance is etched into the wrecks themselves. The presence of a dedicated pump well, a sump built into the very keel of the ship where water would naturally collect, shows just how standard and integrated this equipment had become in Roman and medieval vessels. It was a permanent, architectural acknowledgement of a perpetual threat. In our world of silent, electric bilge pumps that switch on automatically, we have lost the visceral urgency of this manual struggle. Yet the principles of these human-powered systems are experiencing a quiet revival. Engineers designing for remote communities and emergency response are now looking at these ancient pump designs for their utter reliability, their independence from fragile power grids, and their repairability with the most basic tools. Managing the slow seepage of water was a constant battle, but it was nothing compared to the sudden, catastrophic violence of a storm-driven wave crashing over the deck. A storm's fury could snap a mast and shred sails, but the most insidious threat was being turned broadside to the waves. In that helpless position, a single roller could capsize the mightiest vessel. The ancient solution was not to fight the ocean's power, but to borrow a small piece of it. Crews would deploy a sea anchor, a large canvas bag, or a heavily weighted plank streamed from the bow on a long, heavy line. This simple device created immense drag in the water, acting as a submerged brake that slowed the ship's violent drift and, most critically, kept its bow stubbornly pointed into the oncoming waves. A veteran sailor would confirm that a properly set sea anchor transforms a potential catastrophe into a merely uncomfortable ordeal, a technique every blue water sailor should know. The physics are a masterclass in passive control. The sea anchor does not stop the ship, it simply creates a pivot point far ahead of the hull. As the wind and waves try to spin the vessel, the relentless pull from the deep forces the bow to remain aligned, allowing the ship to ride over the crests instead of being rolled over by them. Construction was a matter of using what was on hand. A spare sail could be bundled and weighted to create a drogue, or a heavy stone with a hole drilled through it could be lowered on a cable, its rough surface creating enough friction in the water to stabilize a small merchantman. Historical accounts from Indian ocean traders describe precisely this practice, using large, perforated stones as drogues to survive the violent squalls of the monsoon. In our modern era, where the instinct is to use engine power to punch through a storm, this ancient technique poses a vital question about redundancy. What happens when the engine fails or the fuel runs out? The sea anchor requires no power, only a simple understanding of the sea's own forces, offering a timeless and utterly dependable plan B for survival. Keeping the ship pointed correctly was a life-saving maneuver, but it did nothing to repair the damage a storm could inflict on the hull itself. Every ship carried its own hospital within its hold. Tucked away near the keel was a comprehensive repair locker, a collection of spare planks, pre-carved tenons, blocks of pine tar, and coils of cordage that turned the crew into an emergency response team. This was not just a box of supplies, it was a philosophy of design centered on resilience and radical self-sufficiency. A single grounding on an uncharted reef or a collision with driftwood could spell doom, but with this kit, the crew could enact repairs at sea, transforming a potential catastrophe into a manageable delay. The ship itself was designed to facilitate this. Planks were often secured in ways that allowed for individual replacement without dismantling half the hull. Frames were spaced to provide clear access to the inner skin of the ship. A shipwright working on a historical reconstruction captured the ethos perfectly, stating that their ships were designed to be fixed by the crew with basic tools, a philosophy of repairability that is the antithesis of our disposable culture. The contents of this maritime first aid kit were meticulously chosen. Spare planks were often shorter sections of the same woods used in the hull, pre-shaped to approximate common curves. Pre-formed tenons, ready to be driven into new Mortise slots, were essential for rejoining severed planks. Jars of heated tar and wax were kept for emergency caulking, while rolls of spare sailcloth and lashing cordage addressed everything from a torn sail to a broken oar. For damage below the waterline, ancient mariners displayed breathtaking ingenuity. Historical accounts suggest the use of primitive diving bells, likely inverted pots filled with air, to give a repair crew precious minutes to work on a breached hull just below the surface. In other cases, skilled free divers would descend to stuff gaps with tarred wool or hammer a temporary patch over a leak, all while holding their breath. The very existence of long-distance explorers like Pythias of Massalia, who sailed from the Mediterranean to the British Isles and possibly beyond, is a testament to this capability. His journey would have been impossible without a vessel and crew prepared to perform major surgery on their own ship in the middle of the ocean. This deep knowledge of materials, especially wood, and how to mend it under duress poses a stark challenge to our modern world. How can we design our own vehicles, our infrastructure, and even our consumer goods to be more field repairable? When a smartphone or a tractor becomes a sealed black box, we surrender not just our ability to fix things, but a fundamental piece of our self-reliance. This intimate, hands-on relationship with repair forged a different kind of knowledge, a tactile understanding of how materials behave under stress that guided the entire construction process from the very beginning. The logs did not go straight from the forest to the shipyard. Many began a transformation that could last for years, submerged in the silent, cold darkness of a river or bog. This was the art of selective timber curing, a patient process that turned raw wood into a marine-grade material through controlled decay. By deliberately leaching out the very substances that attract insects and fungi, the tannins and sugars, these ancient craftsmen were preemptively rotting the wood in a safe, managed way, leaving behind a cellulose skeleton that was far more resilient. A wood scientist analyzing ancient samples observes evidence of controlled biodegradation that actually improved performance, a concept we are now exploring with modern biotreatments. The methods were as varied as they were ingenious. Water seasoning involved weighing down logs in flowing rivers for months or even years, allowing the current to slowly wash away the soluble compounds that would otherwise lead to decay. In other regions, builders practiced bog seasoning, sinking timber into peat bogs where the acidic, low-oxygen environment preserved the wood while simultaneously toughening its fibers. Air drying was its own science, with stacks of lumber arranged in specific configurations to promote even airflow and prevent warping, often under shaded shelters that protected the wood from the cracking heat of the sun. Some cultures employed smoke curing, exposing timber to the fumes of slow-burning fires, which deposited creosote and other natural preservatives that acted as powerful insecticides and fungicides. The choice of treatment was a precise decision based on the species. Elm, for instance, responds beautifully to water seasoning, while oak gains superior durability from slow air drying. The legendary timbers of the Swedish warship Vasa, which survived 3 centuries on the seabed before its recovery, stand as a testament to this legacy of careful preparation, their resilience forged long before the first plank was ever shaped. In our world of pressure-treated lumber and chemical dips, where we force changes upon wood in a matter of hours, what profound strength are we sacrificing for the sake of speed? This reverence for the material's inherent potential was matched only by the reverence for the tool that unlocked it. The adze was the shipwright's true voice, a curved blade on a long handle swung in a continuous, rhythmic arc that bit deep into the timber. With each precise strike, the craftsman was not just cutting wood, he was reading its story, feeling the resistance of the grain, and adjusting his swing to follow the natural flow of the fibers. This intimate dialogue between human, tool, and material produced a surface that was uniquely compressed and sealed. A master carpenter working with these traditional methods would confirm that the adze leaves a finish almost like it has been sanded and varnished in one step, a surface that naturally sheds water and resists the initiation of rot far better than a surface torn by a power saw. This was not crude chopping, it was a high art form. Different adzes served specific purposes, from the heavy hewing adze for roughing out large timbers to the delicate finishing adze that could leave a surface as smooth as planed wood. The froe was another genius of simple mechanics, a blade struck with a mallet to rive or split planks along the grain, following the wood's own weakest path to create boards of incredible strength. The draw knife, pulled toward the user, allowed for fine shaping of curves, while the auger, a simple drill bit turned by a bow or a T-handle, bored clean holes without burning or splintering the surrounding wood. The metallurgy behind these tools was equally sophisticated. Blacksmiths forged blades from high-carbon steel, carefully tempering them to hold a razor-sharp edge that could be honed on a whetstone carried in the craftsman's apron. The evidence of this mastery is etched into the very wood it shaped. On the timbers of the Newport medieval ship, you can still see the characteristic scalloped marks left by the adze, a perfect surface that has survived centuries of immersion. This creates a profound question for our modern design processes. When the person who designs a ship's hull has never felt the feedback of an adze striking oak, when there is a complete disconnect between the digital model and the physical act of making, are we inevitably creating designs that are less optimized, that fight the nature of the material rather than working with it? The tools gave each piece its purpose, but the final test was in their perfect union. A master shipwright's vision was no longer confined to his mind's eye or a few chalk marks on the floor. It was captured in a physical template, a full-size wooden pattern that guaranteed every frame in the ship would be a perfect symmetrical match. This was the birth of mold-based framing, a quiet revolution that balanced the soul of the artisan with the demands of scale. On the vast lofting floor of a Roman shipyard, the entire ship would be drawn at a 1-to-1 scale, a giant blueprint etched in chalk and charcoal. From this master drawing, thin wooden templates were carefully cut, each one defining the exact curvature of a specific frame. A historian of engineering points out that the mold allowed for the delegation of work. Less experienced apprentices could now build frames with absolute accuracy by simply tracing the template onto heavy timber, dramatically scaling up production without sacrificing the integrity of the design. This was the crucial pivot from purely empirical, build-as-you-go methods to a planned, predictable process. The materials for these templates were humble, often thin planks of fir or pine, but they represented a profound leap in thought. They codified the hard-won knowledge of generations, freezing the perfect hull form into a reusable guide. This system directly enabled the frame-first construction method, where this prefabricated skeleton was assembled first, and the planks were then fastened to it, a method that would eventually come to dominate European shipbuilding. Archaeological remains at Roman port sites like Ostia show clear evidence of these standardized practices, suggesting an almost industrial level of organization for building the empire's vast merchant and military fleets. This blend of craft and systemization forces a difficult question for our own time. In our pursuit of maximum efficiency through automation, have we tipped the scale too far, losing the intuitive adjustments of the master craftsman? Or is the ideal balance still waiting to be found, a harmony where technology serves to amplify skill rather than replace it? With this symmetrical skeleton now standing in the yard, the builders could return their focus to the ship's outer shell, applying each plank with the confidence that the form beneath was perfect. That ridged, overlapping surface of a clinker hull was not just a style, it was a philosophy of strength born from necessity. In the violent, unpredictable waters of the North Atlantic, a Viking longship needed to be more than strong. It needed to be alive, twisting and flexing over waves like a sea serpent. Each plank or strake overlapped the one below and was riveted fast, creating a hull that was essentially a unified, corrugated shell. This was a ship built from the skin inward, its strength distributed across the entire surface. A naval architect comparing the two methods might describe clinker as a flexible exoskeleton, absorbing and dissipating energy at every seam. The tools for this were as direct as the method itself, requiring drills for rivet holes and hammers to clinch the iron nails that pulled each plank tightly over its neighbor. Sealing these overlaps was an art. Workers would hammer tarred animal hair or wool into the seams before the next plank was laid, creating a gasket that compressed with every movement of the hull. Hydrodynamically, the ridged surface created a turbulence that actually reduced overall drag in certain conditions, allowing these vessels to slice through choppy seas with a unique stability. The Oseberg ship, with its elegantly overlapping planks sweeping upward into those iconic spirals, is the ultimate testament to this approach, a vessel designed not for calm harbors but for the open fury of the ocean. Across the sea, in the sun-drenched and generally calmer Mediterranean, a different philosophy took hold. Carvel construction presented a perfectly smooth hull, its planks laid edge to edge on a pre-built, rigid internal skeleton. This was an endoskeleton, a frame that bore the primary loads to which the skin was attached. The result was a hull form that was far more efficient for carving through water, offering less resistance and thus greater speed under sail, and a vast, unobstructed interior space perfect for stacking amphorae or mounting heavy cannon. The skills required shifted from the holistic vision of the clinker builder to precise joinery and frame making. The sealing method was different too, relying on caulking forced into the narrow gaps between planks, often a mixture of tar and oakum that would swell when wet to create the seal. This smooth skin was ideal for the trade routes of the Mediterranean and the eventual voyages of discovery, embodied by ships like the Portuguese Carvel and the Spanish Carac. These were the cargo planes and warships of their day, optimized for capacity and firepower on long, mostly downwind passages. So, the ancient choice between clinker and carvel forces a modern reflection. In our search for optimal design, are we chasing a single, universal solution when the true wisdom lies in maintaining a diverse toolkit of specialized answers, each perfectly suited to its specific environment? This external shell, whether ridged or smooth, derived its ultimate resilience from a hidden internal network. Deep within the ship's hull, an unseen lattice of wooden sinews fought a constant, silent war against the ocean's twisting power. These were the knees and riders, a complex system of diagonal and lateral braces that transformed a wooden shell into a unified structural entity. Think of them as the ship's interior skeleton, not just vertical ribs, but a three-dimensional web of angled supports that locked every component in place. A structural engineer marveling at this design would note that ancient shipwrights had an intuitive grasp of triangulation, creating a wooden truss that distributed stress far more efficiently than a simple box frame. The genius was in the variety. Hanging knees were mounted vertically, connecting the beams to the sides, while lodging knees were fitted horizontally, bracing the deck against the hull. Standard knees, often the most crucial, were those perfect, naturally curved timbers fitted into the angles between the frames and the deck. Each type addressed a specific force, whether it was the upward lift of a wave or the sideways racking of a gale. Their placement was a masterclass in anticipating failure. The area around the maststep, where the immense weight and thrust of the mast transferred into the hull, was always reinforced with a dense cluster of these knees. Similarly, the stern, a complex junction of curving planks, relied on a tailored network of riders, which were essentially extra frames inserted between the main ones to resist crushing pressures. The 17th century flight, a Dutch cargo vessel, represents the ultimate expression of this principle. Its hull was a forest of internal bracing, a redundant network that allowed it to carry heavier loads across longer distances with remarkable durability. This ancient approach to creating resilience through distributed, redundant support poses a critical question for our own structural engineering. In a world of minimalist design and optimized materials, have we sacrificed the forgiving strength of a system where multiple elements share the load, ensuring that the failure of one single component does not lead to catastrophic collapse? All of this intricate bracing ultimately served one paramount purpose: to manage the awesome forces channeled down from the ship's single most vital component. The maststep was the ship's heart, a single point of wood that bore the fury of the wind. Every gust, every shuddering impact of a wave channeled down the towering spar and focused its entire force into this one critical junction. If it failed, the mast would punch through the hull like a spear, or simply topple over the side, leaving the ship a helpless driftwood. Ancient shipwrights treated this component not as a mere socket, but as the central anchor of the entire vessel's integrity. They understood that the immense dynamic loads required a solution of overwhelming strength, a philosophy of deliberate over-engineering that prioritized survival above all else. A modern yacht designer observing these ancient structures might reflect that we sometimes sacrifice too much safety in our relentless pursuit of lightness and speed. The Maststep was the antithesis of this trend, a component built with a generous margin for the unexpected. The evolution of its design reveals a continuous search for better ways to distribute these crushing forces. The earliest examples were simple mortises carved directly into the keel timber itself, but as ships grew larger and sails became more powerful, this approach was no longer sufficient. Builders began crafting massive, specially shaped timbers, often of a harder, more durable wood like elm or oak. This block, itself several feet long, was then locked into the keel, its grain oriented to best handle the compressive and twisting forces. The entire assembly was frequently bound with bronze or iron straps, creating a composite structure of wood and metal that spread the mast's load across the entire length and breadth of the ship's backbone. We see this masterful engineering in the wrecks of Phoenician traders, vessels built for long, perilous voyages across the open Mediterranean. Their mast steps are monumental constructions designed to withstand the relentless drive of their large, powerful sails. These were not just pieces of wood, they were the core of the ship's power plant, the anchor that translated the wind's invisible energy into forward motion. This ancient focus on reinforcing critical load points poses a stark challenge to a modern engineering ethos that often seeks to shave away every possible gram. What is the true cost of this optimization? When we push materials to their absolute limits, are we inadvertently designing fragility into our systems, leaving no room for the rogue wave, the sudden squall, the unpredictable event? The Maststep stands as a silent argument for the wisdom of robust, resilient design, a reminder that some components are too vital to ever be considered lightweight. That towering mast was a masterpiece of composite engineering long before the term was ever coined. Relying on a single, perfect tree was a fantasy for most shipwrights, so they invented a superior alternative, the made mast. This was a spar built up from multiple pieces of wood, carefully scarfed and bound together with miles of rope into a single, unified structure that was stronger and more resilient than any solid log. The true genius lay in its engineered flexibility. A traditional spar maker would describe a made mast as having a life of its own, designed to bend and spring back in a controlled manner, absorbing the wind's violent gusts instead of resisting them until it snapped. This was the ancient world's carbon fiber, a composite material tailored for performance. The method of joining these pieces was critical. Craftsmen used complex scarf joints, cutting interlocking fingers or wedges into the ends of the timbers. These joints were then smothered in tar and pressed together, their surfaces perfectly mated before being lashed with coil upon coil of rope. This rope, often the finest hemp or coir, was wound on under immense tension, sometimes with a specialized tool called a Spanish windlass that twisted the rope tighter and tighter, compressing the entire assembly into a single monolithic beam. The selection of wood for each part was a science. A lower mast needing immense stiffness might be built from dense oak, while a long yardarm, which had to be light and flexible, was crafted from resilient spruce or fir. The iconic Lateen yards of Adze house, sometimes longer than the vessel itself, are breathtaking examples. These colossal spars, bending in a graceful arc under a full press of sail, could never have been sourced from a single tree. They were living proof that by combining materials intelligently, you could achieve properties nature alone could not provide. In our modern quest for new composites, are we overlooking the profound wisdom in these traditional methods of lamination and binding, where the whole becomes far greater than the sum of its parts? The creation of such a dynamic spar demanded an equally intelligent system of control. That complex web of ropes was the ship's nervous system, a living machine of tension and control. Standing rigging, the fixed network of shrouds and stays, held the masts upright against the relentless push of the wind. Running rigging, the dynamic maze of halyards and sheets, became the crew's direct interface with the sails, allowing them to capture, reduce, or spill the wind's power with a coordinated pull. This was not a collection of random lines, it was a meticulously engineered architecture of force. A rigger on a tall ship would affirm that the rigging is the nervous system of the ship. When it is tuned right, the whole vessel sings. The ancients had an empirical understanding of tension and vector forces that was remarkable. Each component had a singular, vital purpose. The shrouds, thick ropes running from the masthead to the sides of the hull, created a stabilizing triangle that prevented the mast from collapsing sideways. Forestays and backstays managed the fore and aft balance, keeping the massive spar from pitching forward or backward in a heavy sea. The materials for this critical system were chosen with the same care. Hemp and flax provided the ideal combination of strength, flexibility, and resistance to rot, while coir from coconut husks offered legendary resilience in salt water. The true genius, however, was in the connections. The strength of the entire system depended on the art of the knot and the splice. A poorly tied knot could unravel under load, a fate as dangerous as a broken plank. Shipwrights employed a lexicon of secure, self-tightening knots, from the sturdy bowline to the complex constrictor hitch. For permanent joins, they relied on the splice, a method of weaving the strands of two ropes together to create a bond that was often stronger than the rope itself. This created a system with no single point of failure, where stress was distributed evenly across the entire network. The principles of this tension-based design are finding new life today. Modern architects and engineers are looking at these ancient rigging systems for inspiration in building suspension bridges, designing tensegrity structures, and even planning the cables for space elevators. The question is profound: how can we apply this ancient wisdom of distributed, adjustable tension to create buildings and machines that are both incredibly strong and inherently flexible? With this nervous system fully tuned, the ship was a living, breathing entity, but it still needed a way to maneuver through the tight confines of a crowded harbor or a narrow river. A ship becalmed was not a ship stranded. Without a breath of wind, ancient mariners turned to a different kind of engine, one powered by muscle and simple physics. They practiced towing, warping, and kedging, techniques that used ground-based leverage to achieve marine mobility. Think of a massive Egyptian grain barge, its great sail limp, being patiently dragged up the Nile by a team of laborers on a riverbank, a human-powered conveyor belt moving against the current. This was the ancient equivalent of a tugboat service, and it required as much skill and coordination as sailing itself. The key piece of equipment was the kedge, a small, lightweight anchor designed not to hold a ship in a storm, but to be moved. In the warping technique, a ship's longboat would row this kedge anchor far ahead, often several hundred feet, and drop it into the riverbed or seabed. Back on the main vessel, sailors would heave on the line, wrapping it around the capstan, a massive rotating drum turned by men pushing on long bars. With every groaning turn, they would literally pull the heavy ship forward, foot by foot, toward the anchor. To navigate a tight, winding river or to pivot a vessel in a crowded harbor, they would repeat this process over and over, a slow, methodical dance of advance and reset. The equipment was as robust as the method was simple. They needed vast coils of heavy cable, made from twisted hemp or papyrus, strong enough to take the immense strain without snapping. The capstan itself was a masterpiece of mechanical advantage, amplifying the crew's strength enough to move a dead weight of dozens of tons. The proof of its constant use is etched in stone. The massive quays of ancient Carthage, still visible today, are worn smooth with deep, curving grooves, scars from the endless sawing of thousands of ropes used to warp ships into their berths. This was also the primary method for refloating a grounded vessel. A kedge would be set in deep water, and the entire crew would haul, leaning their combined weight into the capstan bars to coax the ship back into its element. In our age of instantly available engine power, we have lost the art of moving large objects with such deliberate, low-energy precision. What simple, human-scale solutions for maneuverability have we forgotten in our reliance on fossil fuels? Knowing exactly how to move a ship was one thing, but its entire economic purpose depended on knowing precisely how much it could carry without sinking. A simple scratch on a ship's hull could mean the difference between profit and a watery grave. Long before the formal Plimsoll line, ancient shipwrights understood the critical relationship between a ship's draft and its stability. They possessed an intuitive, almost visceral knowledge of the exact waterline that balanced maximum cargo with seaworthy safety, a calculation refined through generations of observation and tragic loss. This was hydrostatic knowledge written in experience, not software. A naval surveyor studying ancient hull forms might note that these builders had an unerring feel for the sweet spot, the precise immersion that gave a vessel the buoyancy to ride a swell and the ballast to recover from a roll. This wisdom was encoded in the ship's very design. In the Mediterranean, archaeologists have observed consistent proportions in Roman merchantmen, their length, beam, and depth locked into a ratio that inherently defined a safe load. The master builder might make a single mark with charcoal or a chisel on the planking, a physical line that told the stevedores, load until the sea kisses this point, and not a finger's breadth more. They understood freeboard, the height of the hull above the water, as a direct measure of survival. Too little freeboard, and even a modest wave could wash over the deck, threatening stability and the crew's lives. Too much, and the ship became top-heavy, a precarious tower ready to capsize in a gust of wind. This empirical science was passed down as oral tradition, a set of rules connecting the type of ship, the season, and the nature of the voyage. A vessel heading into the stormy winter Mediterranean would be loaded more conservatively than one plying the calm summer trade routes. This ancient practice challenges a core tenet of modern engineering. Does our reliance on complex digital modeling sometimes blind us to the simpler, more holistic truths that can be grasped by a seasoned eye? Knowing the ship's limit was one thing, but that knowledge was useless without an equally sophisticated method for packing its hold. The silence within a sunken ship's hold tells a story of meticulous order. A ship's survival depended not just on its hull, but on the careful science of how its cargo was packed and secured. This was the art of stowage and the strategic use of dunnage, materials like brushwood, sand, or loose timber placed between and beneath the goods. Dunnage served a triple purpose. It stabilized the cargo to prevent dangerous shifting. It created channels for bilge water to flow freely to the pumps, and it protected fragile items from the constant grinding and moisture that could ruin them in a long voyage. A logistics expert studying ancient trade routes would confirm that the stowage plan was as important as the ship's design. A poorly loaded ship was a doomed ship, regardless of its construction. This was the dynamic management of mass on a moving, tilting platform. Heavy items like amphorae filled with wine or oil were always placed low in the hull, acting as permanent ballast to keep the vessel stable. Lighter goods such as textiles or papyrus were stacked higher, but the true genius was in the dunnage itself. Sand or gravel spread across the bottom provided a level base and aided drainage. Bundles of brushwood were woven between amphorae to lock them in place, creating a single, solid mass that could not slide. Loose timber could be used to shim and brace crates, ensuring that every single item had its own designated, immovable space. The proof of this mastery lies in the Uluburun shipwreck, a Bronze Age time capsule. When archaeologists mapped its cargo, they found a perfectly preserved stowage plan with copper ingots, glass, and ebony all meticulously arranged and separated by dunnage, a load that held fast even as the ship plunged to the seabed. In our modern world of container shipping, where goods are simply stacked in metal boxes, have we lost this nuanced understanding of how to integrate cargo with the very structure of the ship itself? This principle of turning cargo into a structural asset leads directly to the next evolution, when the ship itself became an instrument of force. The bronze ram was an engine of total destruction, a weapon that turned the ship itself into a projectile. Cast in a single piece using the lost wax method, this was not a simple spike but a sophisticated multi-bladed instrument of naval warfare. Its design was brutally elegant, featuring a central point to breach the hull, with horizontal fins above and below to slice and splinter the enemy's planks upon impact. The goal was not to create a neat hole, but to unleash a catastrophic shower of wooden shrapnel and open a massive, flooding gash that would sink a vessel in moments. An expert in ancient naval warfare would explain that the ram was the culmination of the ship's design. Its speed, maneuverability, and structural strength were all focused into that one bronze point. But this fearsome weapon was useless without a hull strong enough to survive its own attack. The force of a ramming strike at speed was immense, and if the attacking ship's own bow shattered, it was a suicide mission. The solution was a massively reinforced stem, an internal lattice of extra timbers and knees that acted as a structural shock absorber. This internal cradle, often built from the hardest available woods, was designed to transmit the colossal energy of the impact away from the point of contact and distribute it safely throughout the entire hull. The Athlete Ram, a rare surviving example recovered from the sea off Israel, provides a physical blueprint of this devastating technology. Its complex shape, with its 3 distinct blades, is perfectly preserved, and the mounting holes show exactly how it was integrated into the ship's reinforced forefoot. This total integration of offensive power and defensive structure forces a modern reflection. How does the need to deliver a powerful blow fundamentally shape the entire design of a vehicle, from its skeleton to its skin? The drive to create an unstoppable weapon inevitably leads to the need for an impenetrable defense. A Roman warship did not just carry soldiers, it became their steel-tipped fist. While the ram was a weapon of destruction, the corvus was a weapon of capture, a boarding bridge that turned the fluid chaos of a sea battle into a controlled, brutal infantry engagement on a floating battlefield. This was a simple machine of profound consequence, a pivoting wooden gangway nearly 36 feet long, mounted to the deck of a Roman quinquereme. At its end hung a heavy iron spike like a monstrous beak. The procedure was terrifyingly efficient. A Roman ship would maneuver alongside its Carthaginian opponent, and at the critical moment, the corvus would be swung out and dropped. The spike would slam down, piercing the enemy deck and locking the 2 vessels together in a fatal embrace. Roman legionaries, the finest heavy infantry in the world, would then charge across this bridge 2 abreast, bringing their land-based combat superiority to a realm where they had been novices. A military historian would note that the corvus was a simple machine that changed the paradigm of naval combat, leveraging Rome's infantry superiority at sea. It was a brutal, pragmatic solution that negated the need for complex naval maneuvers, a domain where the experienced Carthaginians excelled. The operational genius is clear, but the engineering trade-off was severe. The corvus and its heavy base structure added immense weight high above the waterline, making the ships dangerously top-heavy and vulnerable to capsizing in rough weather. Historical accounts suggest that entire Roman fleets were lost to storms, their stability compromised by the very device that had won them victories. This was not the only boarding tool in the ancient arsenal. Grappling hooks thrown by hand or launched from engines were the universal method for snagging an enemy ship and reeling it in. Some Hellenistic kingdoms built massive warships equipped with actual wooden towers from which archers and artillery could rain down projectiles, turning the ship into a mobile siege platform. The corvus itself was a flash of brilliant, if flawed, innovation. Its successful deployment in the First Punic War, particularly at the Battle of Mylae, allowed the nascent Roman navy to defeat the far more experienced Carthaginian fleet, securing Roman dominance over the Mediterranean. Its eventual abandonment due to its stability issues shows a fascinating cycle of technological adaptation and its unintended consequences. This ancient practice of designing a vessel specifically as a troop deployment platform echoes powerfully into the modern age. How does the need to carry and deploy personnel, whether Marines, pilots, or astronauts, fundamentally shape the design of our own platforms? The aircraft carrier, with its vast, flat deck and complex launch systems, is the direct spiritual successor to the corvus-equipped quinquereme, a ship whose entire form is dictated by its function as a mobile base for projecting power. Even the design of a future spacecraft intended for planetary landings must solve the same core problem: how to safely deliver personnel from a mobile platform to a specific point of engagement. This principle of the ship as a specialized habitat extends far beyond the grim necessities of war, reaching its most extravagant expression in vessels built not for battle, but for pure, opulent pleasure. Gold leaf shimmered across the hull of Pharaoh Cheops' funerary ship, a divine armor that was far more than royal vanity. This was the pinnacle of decorative and protective sheathing, where a vessel's outer skin became a statement of power and a practical shield. For prestige craft like royal barges and imperial pleasure yachts, shipwrights clad the hull in materials of breathtaking value: thin sheets of hammered gold, intricately carved ivory plaques, or panels of fragrant, rare cedar. The brilliance of this practice was its inherent multifunctionality. The opulent display projected absolute authority, but the materials themselves were carefully selected for their physical properties. An art historian specializing in maritime culture observes that the sheathing was a statement of power, but the materials chosen often had practical properties, like cedar's natural resistance to rot. Ivory and dense, exotic woods created a hard, slick surface that was difficult for marine borers to penetrate, while precious metals formed an impervious barrier against the water itself. Applying these delicate materials to a hull that constantly flexed and worked in the waves was a mastercraft. Artisans used complex natural adhesives, recipes of tree resins, beeswax, and animal glues that remained flexible after they cured. They developed techniques for laying the sheathing in overlapping scales or small panels, a configuration that allowed the underlying hull to move without cracking the precious veneer. The symbolic language was as precise as the craftsmanship. In Egypt, gold represented the flesh of the gods and the imperishable nature of the sun, making a gold-sheathed ship a literal vessel of divinity. In Rome, the use of citrus wood from North Africa was not just about its beauty, but a direct display of imperial reach and control over distant, valuable resources. The legendary ship of Cheops, disassembled and buried for his journey to the afterlife, stands as the ultimate example, its gold sheathing ensuring his majestic passage for eternity. This seamless blend of high art and practical engineering compels a modern question. In our own designs, from architecture to consumer products, have we foolishly divorced aesthetics from utility? Could the surfaces of our buildings, our cars, or our devices be treated in ways that are not only beautiful but also actively protect, preserve, and enhance performance? This pursuit of perfection, whether for a pharaoh's eternity or an emperor's afternoon cruise, culminated in the moment the completed vessel first met the water. The moment a ship first met the sea was a controlled collision between land and water. On a carefully engineered slope of timber called the launching ways, the completed hull rested in its wooden cradle, its massive weight held back only by a series of strategic triggers. The groundways themselves were a temporary masterpiece of civil engineering, a track of heavy beams packed with earth and stone to create a perfectly smooth, consistent incline leading directly into the water. The precise angle was everything, a calculation born from generations of experience. Too steep, and the ship would plunge into the water with catastrophic force, shuddering its joints apart. Too shallow, and it would stall in humiliating silence, stranded on the brink of its destiny. To manage the colossal friction, workers slathered the ways with animal tallow or olive oil, creating a slick surface for the cradle to slide upon. A project manager for a modern shipyard might reflect that a successful launch has always been a tense moment. The ancient methods, while simple, were based on a solid understanding of physics and required immense coordination. The launch was a symphony of controlled release. At the command, crews would knock out the final wooden supports, and the ship, often weighing hundreds of tons, would begin its slow, then accelerating slide. The groan of timber and the scent of scorched fat filled the air as the hull picked up speed, a moment of pure, harnessed kinetic energy culminating in a tremendous splash as it settled into its natural element. This was never a private affair. Historical accounts of Phoenician or Greek launches describe them as great public ceremonies, accompanied by prayers, sacrifices, and the cheers of the entire community, a collective release of breath after months of labor. The entire operation, from the precise construction of the ways to the synchronized pull of ropes and knock of hammers, was a lesson in high-stakes project management. Every participant knew their role, every contingency was considered, and the entire process was built around a single, irreversible moment of truth. What fundamental principles of planning and execution can we learn from these well-orchestrated operations, where failure was not an option and the transition from one state to another had to be flawless? Once afloat, the ship was no longer a static construction but a living entity, its every characteristic now open to the judgment of the waves and wind.